All right, hello, differential equations, chapter 7, Laplace transforms. We're in the middle of 7.2. We learned how to do some Laplace transforms. We didn't learn to do some inverse Laplace transforms. But here comes the big one. Can we do the Laplace transform of a derivative? So the way this formula is written, and this is in the table, it's number 50 something in the table. Hang on, I'm sorry, it's in the table, and it's number 58 in the table. In the table they use function f, I use the function y here. And you know, when I put an n in parentheses, it's not an exponent n, it's a derivative. So this is the nth derivative of some y function of t. And the rule is, if you're doing the nth derivative, it's s to the n times big Y of s minus s to the n minus 1. The s goes down a power. And this is little y of 0. Now, that's an initial condition from the dE. Minus s, the s goes down another power, and then the next initial condition jumps on there, times y prime of 0. Minus all the way down to where s is gone, and you have your last initial condition. So that's the formula for an nth derivative. It's kind of complicated. So what we, in practice, in reality, we do a first derivative or a second derivative. Let's try. A first derivative would just be s times big Y of s, just an s to the first, big Y of s. And then we only have one initial condition, y of 0. The s is gone away, and there you go. The pattern's over. Here, let's try it with a y double prime. If I had a y double prime, taking the Laplace of a y double prime, it's s squared big Y of s minus s times y of 0, that first initial condition. Notice the s is decreasing in power. Finally, it goes away, and there's the last initial condition, y prime is 0. So we often do y primes, y double primes. Let's just try a y triple prime for fun. If I had s cubed, I guess it'd be s cubed, big Y of s. I'm learning the pattern. S squared times the initial condition. The s's keep decreasing. The initial conditions keep jumping on there. The next one, that was y of 0. This is y prime of 0. Finally, there is no more s's, and we get the last initial condition, y double prime of 0. That's what happens when you're taking the Laplace of a y triple prime. So these are good. This is good. This is handy little rules right here. You should definitely pause, write that down. But I made up a little example here. So now I want to solve a differential equation. Here we go. We're going to solve a differential equation. Here we go. This is going to be awesome. This is what happens at the end of 7.2. There's a lot more things to learn up in 7.3. But at the end of 7.2, you get to solve a few differential equations. I made this one up. Y double prime plus, I hope it works, 9y equals 4t. And I got some initial conditions. Y of 0 is 1. Y prime of 0 is 1. All right. All right. That looks like a differential equation. This is brand new. How do you solve a differential equation using Laplace transforms? Well, here's what you do. You walk into the dE and you take the Laplace. You just take the Laplace of everybody, the whole differential equation. So you take the Laplace of everybody. Now, I don't want to write here. I'm just going to write it like this. I'm taking the Laplace of everybody. So I'm taking the Laplace of a y double prime. Well, I just learned that 2 seconds ago. Here's what it is. It's s squared big Y of s minus s y of 0 minus y prime of 0. That's the Laplace of y double prime. Then I walk in here and I take the Laplace of the 9 times the y. Now maybe hopefully you remember, I can just take the 9 out, and then when I'm taking the Laplace of a function called y, I mean it's not the variable, it's not the independent variable t. That's different. It's the function y, and we just call it big Y of s. I was talking like that in my last video. Now I go to the other side of the equation. Now I am taking a Laplace of a function of t. And I think the Laplace of t, if I can look it up in my tables, I think it's 1 over s squared. Of course, multiplied by the 4 would be a 4 over s squared. So that's the game. You take the Laplace of everybody. I took the Laplace of each one of these terms in the differential equation. The Laplace of a derivative is a kind of a long, complicated thing. Now, we should fill in these initial conditions. And then the other thing we do is we solve for, the idea is we're going to solve for big Y of S. You know, if we get big Y of S by itself, I can take the Laplace inverse, which will get me Y of t. By the way, we're solving a differential equation. You know, the goal is to find the function y that satisfies this. So we get big Y of S, we take the Laplace inverse of big Y of S, and that gives me the function y of t. We're done. We solve the dE. Here, I'll help you. Hang on, I'm filling in these initial conditions. S squared big Y of S minus, that's a 1. Right, that's a 1 times S, minus, that's a 1. Plus 9 big Y of S equals this 4 over S squared. You know, I want the big Y of S all by itself. So let's move these terms to the other side. And then what's left is these two terms. And I factor out the big Y of S, and I'm left with an S squared plus 9. Now over on the other side, there's this 4 over S squared. And I move this over, it's a positive S. I move this over, it's a positive 1. Move those to the other side. I'm trying to get big Y of S by itself, so I'm going to divide by this. Big Y of S is 4 over S squared plus 9. I just divided by S squared plus 9. I'm dividing that guy by S squared plus 9, that S. And I'm dividing this 1 by S squared plus 9. So that's the game. You get big Y of S all by itself, and now you Laplace the thing up here. Now you Laplace inverse it. Laplace inverse this thing, which gives you the answer y of t. You're also then, what you're doing is you're going over here and you're Laplace inversing all these. That'll get you back to functions of t, which will be the answer. So you do the Laplace inverse. That's the strategy. That's the method. Laplace the dE, do this work, get big Y of S by itself, Laplace inverse the big Y of S and the other side, and you're done. You've solved the differential equation. It's a very unique method. It's a cool method. That's a little tricky. That's not on the top of my head. I'm gonna leave that alone for just a minute. Let me jump over here. That's easy. I got that one memorized. That is the cosine of 3t. He's classic. That is the cosine of 3t. I just Laplace inverse that. That's with the number on, with the S on top, it was cosine. With the number on top, it's a sine. It's a sine of 3t. But if I remember the way sine works, it wants a 3 on top. So I'm going to have to multiply by a 3 and put a 1/3 out front. Then it's the sine of 3t. Did you follow that? I had to put a 3 up there to make it the sine of 3t. But putting a 3 up there required me to put a 1/3 out front. So it's 1/3 sine of 3t. Yeah, those are done. I Laplace inverse to those. This one I got to look up here. I'm not familiar with that guy. I hope he's back here. I'm looking for an S squared. Oh, I see something here. Number 31. He looks like number 31. That's going to take a little work here, though. He looks like number 31. S squared plus k squared. Number 31 wants a k cubed on top. Now my k is a 3. So it wants a k cubed on top. That's 27. So what do? Put a 27 on top? Let's pull the 4 out of the way. I'll pull the 4 out of the way. I'll put a 27 on top. But that means I'll have to divide by 27 out front. And then it's number 31. Pull the 4 out. I do this, I'm not writing too much. Pull the 4 out, put a 27 up there, and then it's number 31. And so I have to put a 1/27 out front. So now it's number 31. What is number 31? Number 31 is kt, the k was a 3, kt minus sine kt, minus the sine of kt. Ta-da! We've just solved the differential equation. You know, the truth is I could distribute that 4/27. I could combine a couple like terms. I could do a little cleaning. I could combine that sine 3t with this sine 3t and collect a couple like terms to clean this answer up. But the video's getting long already. Hey, that's cool, dude. We solved a differential equation using Laplace transforms. It's so interesting, you know. Notice the initial conditions are built into the process. You know, at the end, there's no C1 or C2. We don't have to find, you don't have to apply the initial conditions. They're kind of, it's done for you somehow. And it feels like it's very algebraic. You know, it feels like you're not doing any calculus. You're not doing any integrating. But when you do a Laplace transform, you are integrating. But we're just using the tables. You know, by definition, the Laplace transform was an integral. Then we finagle it around, then we do the Laplace inverse to get me back to the solution to the dE. So anyway, that's awesome. Good luck.